Tonight, we are going to cross a line that the universe has drawn in permanent ink. Not a metaphor, a thought experiment, a real boundary written into the fabric of space-time itself, beyond which the rules that govern everything you have ever known, light, time, cause and effect, simply stop applying in any way we can follow. That boundary has a name. Physicists call it the event horizon, and what lies on the other side of it is the most honest mystery in all of science. Not a mystery we haven't solved yet. Not a mystery waiting on a better telescope or a faster computer. A mystery the universe has specifically and permanently arranged for us never to solve, no matter how intelligent we become or how long we persist. A black hole is the only place in existence where the cosmos has locked a door, swallowed the key, and then erased the concept of doors entirely. By the end of tonight, you are going to understand what we know about what waits inside, why every theory we have breaks down the moment we try to look, and why the most important answer in all of physics may be the one we are permanently forbidden from ever reaching. Before we go further, if you love sitting with the deep questions of the universe as much as we do, take a second to like this video or subscribe. It is a small thing, but it helps these explorations reach more curious minds now. Let us begin. To understand what is inside a black hole, you first have to understand what a black hole actually is. Because name is almost perfectly misleading. It suggests a hole, an absence, an emptiness in space shaped like a tunnel. None of that is correct. A black hole is not empty. It is the opposite of empty. It is the most extreme concentration of mass the universe is capable of producing. It is not a void. It is a wound. To understand how that wound forms, you have to understand what stars are doing every moment of their lives. A star is a war. Specifically, it is a war between two forces that never stop fighting each other for as long as the star exists. On one side is gravity. Gravity is pulling every atom of the star inward toward the center, trying to collapse the whole enormous thing into a single point. On the other side is the energy produced by nuclear fusion at the star's core. Enormous quantities of heat and light and radiation pressing outward in every direction, trying to expand the star and blow it apart. For most of a star's life, these two forces cancel each other out. Gravity pulls in, fusion pushes out, the star holds its shape. It sits in a kind of perpetual draw, a stalemate that can last millions or billions of years, depending on the star's size. But the stalemate cannot last forever, because fusion is not free. It requires fuel, and the fuel is hydrogen, which the star is burning through every second of its existence, converting it into helium, and then into heavier and heavier elements as the hydrogen runs low. The fusion process works its way up the periodic table, fusing helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. And when the core fills with iron, the war ends. Iron is the graveyard element. It is the one element in the universe that cannot be fused further to release energy. Fusing iron actually requires energy rather than producing it. So when the core goes iron, the fusion engine that has been holding the star up against gravity for its entire life simply switches off. And in that moment, gravity wins. The collapse happens in less than a second. The core of a massive star, something that may have been the size of Earth, collapses to a ball, roughly the size of a city, in less time than it takes you to blink. The outer layers, no longer supported, fall inward at a fraction of the speed of light, and then violently rebound in one of the most energetic events in the universe, a supernova, a detonation so bright it can briefly outshine the entire galaxy it lives in. But that is the outside. The outside is the spectacle. The inside is the story. What remains at the center after the explosion is a core of matter compressed beyond any limit we have language for. In some cases, what remains is a neutron star, an object roughly 12 miles across, containing more mass than the entire sun. A teaspoon of neutron star material would weigh roughly 4 billion tons. It is matter so compressed that electrons and protons have been crushed together into neutrons, the entire object essentially one enormous atomic nucleus. But if the original star was massive enough, even that is not the end. Even the neutrons cannot hold. Gravity continues to win, the object continues to collapse, and at some point, it reaches a density at which the gravitational field it produces becomes so intense that light itself, the fastest thing the universe permits to exist, can no longer escape. That is a black hole. Not a hole, not an absence, a thing. A real physical object with mass, with gravity, with a location in space. But a thing wrapped in a surface from which nothing that crosses it can ever return. That surface is the event horizon, and the event horizon is where our knowledge ends. Sit with that for a moment, because it is genuinely strange. We can observe black holes. We can measure their mass. We can watch stars orbit them. We have photographed the glowing ring of superheated gas that surrounds them. In 2019, the Event Horizon Telescope showed us the shadow of a black hole 65 billion times the mass of the Sun, at the center of a galaxy called Messier 8755 million light-years away. In 2022, they imaged Sagittarius A, the 4 million solar mass black hole at the center of our own Milky Way. We know black holes exist. We have seen them, in the sense that we have seen their effects and their immediate surroundings with extraordinary precision. And yet we know almost nothing about what they actually are on the inside, because no information from inside the event horizon can ever come out to tell us. This is not a failure of technology. It is a failure of physics to permit the information to travel. Think carefully about what that means. Every time you learn something about the world, you are receiving information. Light bounces off an object and reaches your eyes. Sound waves travel through air and reach your ears. The universe communicates with you constantly, delivering information about what is happening around you through every carrier it has available. Your entire experience of reality is made of information traveling to you from the outside world. Now imagine a region of space from which no information of any kind can travel outward. Not light, not radio waves, not gravitational signals, not anything. A region sealed not by walls or barriers, but by the geometry of space-time itself, curved so severely inward that every possible path forward leads deeper in, never out. That is what the event horizon creates. A one-way door. Matter and light and information can cross it in one direction, falling inward. But nothing can cross it the other way. Once you are inside, every direction, including the direction you would think of as up or out or away, leads further in. Not because the black hole is pulling you, because space-time itself is oriented that way. The interior of a black hole is not a place where escape is very difficult. It is a place where the concept of outward has ceased to have meaning. And that is why we cannot know what is inside. Whatever is in there cannot tell us. We cannot send a probe and wait for a signal. We cannot shine a light and watch what comes back. The interior is causally disconnected from the rest of the universe. Events that happen inside a black hole cannot affect anything outside it. They are not simply hidden, they are severed. But we are not without ideas. Physics does not simply stop at the event horizon and throw up its hands. We have two of the most powerful theories in all of science, and we can apply both of them to what might be happening inside. The problem, and it is one of the deepest problems in all of physics, is that they give us completely different answers. The first theory is general relativity. Einstein's description of gravity, published in 1915, is still, after more than a century, the most precisely tested theory in the history of science. It describes gravity not as a force, the way Newton described it, but as a curvature of space-time. Mass tells space-time how to curve. Space-time tells matter how to move, and in the extreme conditions of a black hole, it makes a very specific prediction. At the center of a black hole, general relativity predicts something called a singularity. A singularity is not a place. It is more accurate to say it is the absence of a place. It is the point at which the mathematics of general relativity breaks down completely. Returning values of infinite density and infinite curvature. Infinite, in this context, does not mean very large. It means the equations have stopped producing answers that correspond to physical reality. The theory is telling us it no longer applies. What does a singularity actually represent physically? We do not know. Some physicists believe it represents a genuine feature of the universe, a point where matter has been compressed to literally zero volume and infinite density, where space-time has torn or crumpled into something we have no language for. Others believe it is a signal that general relativity is simply incomplete, that it breaks down in extreme enough conditions, the same way Newtonian gravity broke down when confronted with the very fast and the very massive. The singularity, on this view, is not a real thing but a gap in our theory, a place where a better theory would take over and give a different, finite answer. Both possibilities are extraordinary. One says the universe genuinely contains points of infinite density. The other says our deepest theory of gravity is wrong, in ways we have not yet resolved. Either way, if you fell into a black hole and survived long enough to approach the center, general relativity says, you would reach a point where space and time as you know them cease to exist in any recognizable form. And then there is the second theory. Quantum mechanics is the description of how matter and energy behave at the smallest scales. It governs atoms and subatomic particles and the interactions between them with a precision that is frankly unreasonable. Quantum mechanics has been tested in thousands of experiments and has never been wrong. It is, together with general relativity, one of the twin pillars on which all of modern physics rests. The trouble is that they are incompatible, not just different in their descriptions, fundamentally, structurally incompatible. General relativity is a theory of smooth, continuous space-time. Quantum mechanics is a theory of discrete, probabilistic, fundamentally grainy reality. At large scales, in the realm of planets and stars and galaxies, quantum effects are negligible and general relativity dominates. At tiny scales, in the realm of atoms and particles, quantum effects dominate and general relativity can be largely ignored. A black hole, specifically its center, is the one place in the universe where both theories should apply simultaneously. The mass is enormous, which is general relativity's domain. The volume it occupies is extraordinarily tiny, which is quantum mechanics' domain. To understand what is actually happening at the center of a black hole, you need a theory that unifies both. A theory of quantum gravity. We do not have one. Not yet. Physicists have been working toward it for decades. String theory is one attempt. Loop quantum gravity is another. There are others still. All of them are incomplete. All of them remain unconfirmed. The unification of quantum mechanics and general relativity is probably the deepest unsolved problem in all of physics. And the interior of a black hole is precisely where its absence matters most. So when you ask what is actually inside a black hole, the honest answer is, we need a theory we do not yet possess to answer the question properly. The two theories we have give us their best partial pictures, but both break down in the place where we most need them. There is more, because even before you reach the singularity, the event horizon itself turns out to be the site of one of the strangest and most unsettling puzzles in modern physics. In 1974, the physicist Stephen Hawking made a prediction that shocked the field. He showed, using quantum mechanics applied to the region just outside the event horizon, that black holes are not actually perfectly black. They emit radiation. This came to be called Hawking radiation, and the mechanism behind it is one of the most counterintuitive things in all of science. In quantum mechanics, empty space is not empty. It is a seething, roiling field of quantum activity. Pairs of particles constantly pop into existence and immediately annihilate each other. borrowing energy from the vacuum for an instant, too brief for us to detect under ordinary circumstances. These are called virtual particles, and they are a real and measurable feature of reality. But near the event horizon of a black hole, something unusual happens. A particle pair can form with one particle on each side of the horizon. The particle that forms outside can escape into space. The particle that forms inside cannot. The outside particle carries away energy as real radiation. The inside particle falls inward. The black hole, having effectively lost energy to the escaped particle, gets very slightly less massive. Over an enormous span of time, the process continues. The black hole slowly, unimaginably slowly, evaporates. For a stellar mass black hole, the process takes longer than the current age of the universe many times over. For a supermassive black hole, the timescale is almost beyond language. But the principle stands. Black holes evaporate. And here is where it becomes deeply troubling. Quantum mechanics has a rule, one of its deepest and most fundamental rules. Information cannot be destroyed. Every physical process, no matter how complex or chaotic, preserves information in some form. If you burned every copy of this script, the smoke and ash would still contain, in principle, the information needed to reconstruct what was written. You could never practically recover it. But the information would still exist. Hawking radiation appears to violate this rule, because Hawking radiation is thermal, meaning it is essentially random. It carries no information about what fell into the black hole. As the black hole evaporates and eventually vanishes entirely, it seems to take with it every piece of information about everything that ever crossed its event horizon. The star that collapsed, every atom that fell in afterward, every photon that strayed across the boundary, gone, not hidden, gone. This is called the black hole information paradox, and it is not a minor technical puzzle. If Hawking is right about the evaporation and quantum mechanics is right about information conservation, then one of them must be wrong. But both have passed every test we have ever devised. They cannot both be right, and yet both appear to be right. Physicists have been wrestling with this paradox for 50 years. Several possible resolutions have been proposed, each stranger than the last. One suggestion is that the information is somehow encoded in the Hawking radiation after all, scrambled beyond recovery, but not truly destroyed. Some recent theoretical work, particularly around a concept called the page curve, suggests this might be the case, but the mechanism by which it would work is still not understood. Another suggestion involves what some physicists call a firewall. The idea, proposed in 2012, is that if information must be preserved in the Hawking radiation, then the event horizon is not the quiet, empty place general relativity says it is. Instead, it would be the site of a wall of intense radiation, a firewall, that would incinerate anything crossing the horizon. No quiet passage inside, just destruction at the boundary. The firewall idea is deeply uncomfortable because it contradicts general relativity's prediction that an observer falling into a large black hole would not notice anything unusual at the moment of crossing the horizon. The local geometry at the event horizon of a large enough black hole should feel, in the moment of crossing, not very different from ordinary empty space. The firewall says no. The firewall says the horizon is violent. We do not know which is right. We may not know for a very long time. There is something else worth understanding about what crossing the event horizon would actually be like. Setting aside the firewall debate for a moment, if you were somehow transported to the vicinity of a black hole and began falling toward it, the experience would depend enormously on the size of the black hole. For a small black hole, one with a mass of a few times the Sun, the tidal forces would destroy you long before you reached the event horizon. Tidal forces arise because gravity is stronger on the side of you, closer to the black hole, and weaker on the side farther away. The difference across the length of your body would stretch you vertically and squeeze you horizontally in a process cheerfully call spaghettification. You would be torn into a long, thin strand of matter before you ever crossed the boundary. You would never experience the inside. But for a supermassive black hole, one with millions or billions of solar masses, the tidal forces at the event horizon are actually quite mild. The horizon is so far from the center that the variation in gravity across your body would be gentle. You could fall through the event horizon of a supermassive black hole without feeling anything unusual at all. In that moment of crossing, nothing would signal to you that you had passed the point of no return. The space around you would look and feel like ordinary empty space, and yet everything would have changed. The mathematics of general relativity tells us something strange about what crossing the event horizon means in terms of time. From the perspective of a distant observer watching you fall, you would appear to slow as you approach the horizon, redshifted by the extreme gravitational field, your image growing dimmer and dimmer, frozen at the boundary, never actually appearing to cross. The light, from the moment of your crossing, would take infinitely long to escape to the distant observer, so they would never see you cross. You would appear to be hovering at the horizon forever, frozen in time, slowly fading. But from your own perspective, from the inside, you would cross the horizon in a perfectly finite amount of time. You would feel nothing remarkable. You would still be thinking, still experiencing, still falling. And then you would realize, looking around, that there is no longer any direction you can travel that does not lead you deeper in. The singularity, whatever it actually is not in front of you. It is in your future. All futures inside the event horizon end at the singularity. There is no avoiding it the same way you cannot avoid next Tuesday. You can travel fast or slow. You can move in any direction, but all paths inside a black hole eventually reach the same destination. How much time you would have between crossing the horizon and reaching whatever waits at the center depends on the black hole's mass. For a stellar black hole, microseconds. For Sagittarius A, the 4 million solar mass black hole at the center of our galaxy, perhaps 20 seconds. For a supermassive black hole of several billion solar masses, hours. In those hours, falling freely inward, you could conduct experiments, make observations, think thoughts. You simply could not communicate them to anyone outside. You would be gathering the most extraordinary scientific data in human history, and there would be no way to share a single word of it. The universe has built the ultimate laboratory and sealed it permanently. Some physicists have asked a deeper question than what is inside a black hole. They have asked whether the interior exists at all in any conventional sense. One of the most provocative ideas in recent theoretical physics involves something called the holographic principle. The idea, which emerged from work on string theory in the 1990s, suggests that the information content of any region of space is encoded not in its volume, but on its surface. The information about everything inside a three-dimensional region can be completely described by data on the two-dimensional boundary enclosing it, the way a hologram encodes a three-dimensional image on a flat surface. Applied to black holes, the holographic principle suggests something almost dizzying. The interior of a black hole and everything that happens inside it may be completely equivalent to and completely described by a theory living on the event horizon itself. The three-dimensional interior, in some deep sense, may not be more real than its two-dimensional description. This does not mean the interior is an illusion in any simple sense. It means that reality may be structured in a way where interior and boundary are not different things, but the same thing described differently, like asking whether a piece of music is more real as sound waves or as sheet music. The answer is that they are the same information in different forms. If the holographic principle is correct, then asking what is inside a black hole may be asking the wrong question. There may be a fully equivalent way to describe everything that happens in terms of physics entirely on the outside. The interior would be real in the sense of being a valid description, but it would not be more fundamental than its surface encoding. Most physicists regard the holographic principle as one of the deepest and most compelling ideas in modern theoretical physics. Most also acknowledge that we are very far from understanding what it actually means at the level of physical reality. Let's be honest about where all of this leaves us. We know that black holes exist, and we have observed them with extraordinary precision. We know they have event horizons beyond which nothing can return. We have a theory, general relativity, that describes the space-time geometry of black holes in exquisite detail up to the event horizon, and that predicts a singularity at the center. We have another theory, quantum mechanics, that tells us black holes must evaporate through Hawking radiation, and that information must be preserved. The two theories are incompatible in the extreme conditions of a black hole's interior. We do not have the unified theory of quantum gravity that would resolve the contradiction. And we cannot go and look. That last fact is the thing that makes black holes unlike any other mystery in science. Almost every other question in physics is in principle answerable by observation. We could not observe distant galaxies until we built powerful enough telescopes. We could not observe subatomic particles until we built particle accelerators. The tools were the limitation, and tools can be improved. But no tool can extract information from inside an event horizon. The limitation is not engineering, it is geometry. It is the structure of space-time itself. We are not forbidden from knowing by our technological youth. We are forbidden by the laws of the universe, and there is something both humbling and quietly extraordinary in that. Science is built on the principle that reality is knowable, that if you look carefully enough, measure precisely enough, think clearly enough, the universe will eventually yield its answers. Black holes are the universe's exception to its own rule. They are the one place where nature has said, this far and no further, not because the answer does not exist, but because the answer cannot, by the laws of physics as they are currently understood, reach you. Every other frontier in science is something we have not yet crossed. The interior of a black hole may be the one frontier we are constitutionally incapable of crossing. The universe has hidden something from us, not behind distance, not behind complexity, behind a law. And that distinction matters, because it means that our ignorance, in this case, is not failure, it is a feature of reality. The universe keeps secrets. It keeps at least one of them perfectly, permanently, and by design. We know what is outside a black hole. We know what the approach looks like. We know what the mathematics predicts at the center. We know the paradoxes that arise when we try to reconcile our two best theories about what waits there, and we know that we will never know for certain. The most extreme thing in the universe remains, in its interior, the most mysterious, the place where matter ends, where time ends, where our physics ends, where perhaps everything we think we know about the nature of reality is replaced by something we do not yet have the language to describe. That dark horizon sits out there in the galaxy tonight. There is one at the center of our own Milky Way. There are believed to be millions of smaller ones, scattered through the disk, the collapsed remnants of massive stars that died before our sun was born. They are there right now, silent and dark and patient, curving space-time around them, swallowing light, keeping their secret. And somewhere in that secret, it is possible, some physicists believe it is likely, that the answer to the deepest question in all of physics is waiting: the unification of quantum mechanics and general relativity. The theory of everything, the deepest description of reality we are capable of reaching, locked inside the one place we can never go. There is something almost poetic in that. The universe hides its deepest answer in the one place we are forbidden to look. It puts the final piece of the puzzle inside the box, and then welds the box shut, using the laws of physics themselves. And from the outside, We are left with our equations and our paradoxes and our theories and our wonder. Looking at the dark, knowing that something is there, unable to reach it, and still somehow understanding it better every year. Good night. If tonight gave you a new way of seeing the darkness between the stars, a like or a subscribe would mean a great deal. It helps these explorations reach more curious minds like yours. Until next time, keep looking up.